Okay, welcome everyone to my continuation of what is algebra. Today I would like to tell you something about in some sense, the most important groups ever. Um, Although, of course, most important is a very biased point of view. They're certainly important groups, and you rarely see them in the first class on group theory. I'm not quite sure why. They're pretty easy, we'll see. And basically, almost all finite groups are of this type. We'll also see that. But in some sense, people don't like to present them in the first class on algebra or on group theory because they tend to get pretty big. That's something I will also explain. And what I'm talking about are matrix groups, which is, well, exactly what it says, right? It's groups made out of matrices. So let's get started. So a main question, if you have seen the definition of a group, and you kind of accept that it's a reasonable definition, it's kind of the symmetry of a certain space, for example, would be how can I actually produce groups? So I will show you some multiplication tables in a second, and usually it's not a good idea to write down a multiplication table because then you would need to check, a lot of axioms, whether this is a group. You would need to check those four axioms that you see here. So basically having a multiplication table is, nailing down that you have a multiplication by definition, but you would need to check something like associativity. Unit is usually easy to see, and inverse is also usually easy to see. But in particular, associativity is really a pain, right? If you have a group of order whatever, it already is a n, already the multiplication table is of order n squared, but you have to, for associativity, you have to check a times b times c, so it gets even bigger. So usually it's not a really good idea to just write down a multiplication table and hope that this gives a group. Another reason not to do that is you might be lucky and you might get a group. Of course, it might happen. It, by the way, rarely happens. If you write down a random multiplication table, almost none of them give groups. Uh, anyway, but still, you would get some kind of basically a random group. And the question is, okay, you found a group, but why should that be of any importance? There are quite a few groups out there, so why should this one be in particularly interesting? No, a better way to produce groups, at least for today, would be to consider automorphisms of a given object. So I have object X and then consider automorphisms of that object. I will give you some examples in a second. They're already below it on my slide. But basically then, well, first of all, if your object X was interesting and now you're studying automorphisms of that object, basically the symmetries of that object, then yeah, it kind of makes sense to believe that this could be an important group because you started with an important object. And that's what's happening most of the time. But also, on the other hand, you also get basically all the axioms for free. So composition in this sense, well, you have maps. You can compose maps, right? F times G is just F, well, depending a little bit on your conventions, but let's say F composed with G. And in this setup, associativity is absolutely trivial. It's composition of maps, so nothing to check. By definition, automorphisms are invertible, so that's also easy. And the identity map plays the role of the unit, which is super easy to see, or basically obvious, basically immediate. So there's absolutely almost nothing to check, or basically there's really nothing to check. Let me just say it this way. If you just construct groups by taking automorphisms of a space. And all of you know examples of that. Namely, if you take automorphisms of finite set, what you get are symmetric groups. Right? So symmetric groups permute elements. So just take automorphisms. I could have, by the way, I could have also written permutations. If you want perm of X, which is kind of the same. Automorphisms is a more formal term here. Anyway, automorphisms of a finite set, these are symmetric groups. And yeah, no wonder symmetric groups are so important because there's automorphisms of finite sets. In a very later, at least later in this, in this video series, we will see that actually Galois groups also arise as automorphisms. Basically, automorphisms of roots of polynomials, strictly speaking, then automorphisms of field extensions, but still automorphism groups. More familiar might be automorphism groups of vector spaces. And in this case, X, I just said X is something, right? X is an object, whatever that means. In this case, X has some extra structure. It's a vector space. So I shouldn't consider all maps. I should consider k-linear maps. And then you get, well, of course, a general linear group, which is the first example of a group you ever see in linear algebra already. And more fancy examples along the way. If you would take, for example, automorphisms of projective spaces, you would get projective linear, general linear groups. But don't worry about those too much. There are a lot of things you can play around with. So automorphisms of X, that's always a group. And in a lot of cases, if X has some extra structure, like k-linear, like this one, that I'm going to zoom in a second, um, you can push this to the group as well in some sense. So you would take, for example, X has structure as structure Y. So instead of considering all automorphisms of X, you could consider all automorphisms of X that preserve Y, and usually you also get a group. I will show you examples of these in this video, basically. But let me repeat the main idea. The main idea is, in order to produce groups, you should look at automorphisms of an interesting object. And kind of the most basic examples are symmetric groups, and the in a very similar way, automorphisms of vector spaces are pretty basic examples, and all of you know them from linear algebra, right? That's what linear algebra is basically about automorphisms of vector spaces. Okay, so let's have a look. So the funny thing is, so in a class on group theory, you usually start with this theory of finite groups, and then you think, okay, if I take general linear group, and from linear algebra, you usually know something like general linear group over R. So let's say general linear group, so 2 by 2 matrices, invertible 2 by 2 matrices over R. That's certainly not a finite group, and that's not what I can take this as certainly a group, but maybe not today. So maybe today I would like to stay more with the finite groups. And how do I get a finite groups from matrices? Well, if you use as coefficients not the real numbers, but a finite field, let's say Z mod 2, okay, then you get a finite group. Why is that? Well, this is a finite dimensional vector space over a finite field. Finite times finite. It's big, we'll see it, but it's still finite. In particular, in this case, I've actually illustrated the multiplication table. So let's have a look how this works. So I claim GLN F2, GL2, sorry, GL2 over F2, and F2 is just a fancy way of saying I take Z mod 2 and consider it as a field, so additive and multiplicative. Very confusing, by the way. If you consider it as a group, it's just additive. If you consider it as a field, you take addition and multiplication. Anyway, it just has two elements, 0 and 1. So I can illustrate them by using black and white. So this guy, for example, let's take this one, is secretly the matrix 0, 1, 1, 1. Make some sense, right? 0, 1, 1, 1. And you can check that actually GL2, F2 has only 6 elements, namely those 6 matrices here. Or because it's a multiplication table, they also reappear here, of course. Okay. And the multiplication is multiplication by matrices. So let's have a look whether we understand what's going on here. Let's say I take this element and I multiply it with this element with itself. I claim I get this element. So let's have a look. So 0, 1, 1, 0 times 0, 1, 1, 0. That's by matrix multiplication, you can easily see that this 0, 1 is identity. And yeah, this is this matrix. So this is the multiplication table of this group. And I like to stress again that it's actually not clear at all why this multiplication table should give a group. In particular, in the way I've illustrated it, I'm not referring to matrices at all. I've just some funny rules that apparently define a multiplication. But if you know that this is GL2 of over a finite field, then you're good. It's immediately clear that this is a group. So this is a really good way to produce finite groups, for example, because now I could take GL2 over the field with 3 elements. I could take GL2 over the field with 4 elements. I can take GL2 over the field with 5 elements, and so on. I will get a group. Always. And that's pretty amazing. You can't take GL2 over Z mod 6. Z mod 6 is not a field. and there is no field with 6 elements. So you can take GL2 over what is called FQ, and I'm definitely going to make a video about FQ at one point. And Q is always a prime power, so it's p to the k. In particular, as k is 1, this is just z mod p. Don't worry about this too much. Just think about z mod p for p a prime for now. Take GLN or GL2 or GL whatever and feed in z mod p, and you get a group. And that's obvious if you think about it, that you get a group. What is not obvious is to write down the multiplication table and then from the multiplication table try to see that you get a group. This is already pretty hard here. And actually, secretly, if you want to check this, there's a small number coincidence here. This is actually the symmetric group. But in general, for not small coincidences that appear, those you get actually new groups which you haven't seen before. And in some sense, all groups are of the form GL or something like that. I will comment on that later. But for now, just take it as, oh, this is a really good way to produce groups. Again, so if you want, the link to this picture is in the description below. So this is a multiplication table of not GL, but a little bit smaller, SL. You can also take SL. SL just means determinant 1. If you have a matrix with determinant 1 and you multiply it with a matrix with determinant 1, you get a matrix with determinant 1. So this forms a group. And again, because it's a matrix, you get product and associativity and everything else for free. And now you feed in a finite field. In this case, Z mod 3, right? So the field with 3 elements. And again, some color code applies, but now I have 3 elements. And you write it down, and write down the multiplication table, and you get something of order 24. And it's absolutely not clear why this huge multiplication table, linked in the description, zoom in, have a look, should form any reasonable law at all if you just look at the multiplication table. But if you think of, oh, this is SL2 over F3, then it's immediate. So this is a really, really powerful way to construct groups, in this case, finite groups, or groups in general. So it's very important. Just to, it gives you a nice class, a lot of classes of groups. I will show you some more in a second. But kind of the formal statement I would like to sell you today is not quite what I want to say in the end, but kind of something you see very often in a class on first class on groups, slightly differently formulated. But basically, there's Cayley theorem, or a variant of Cayley theorem, which says a finite group of order n can always be realized as a subgroup of matrices. And this is usually called finite groups are linear. Linear is referring to that, well, it's a subgroup of matrices. That's not quite Cayley theorem. Cayley theorem is a little bit stronger. Cayley theorem would say not just of GL and Z, but actually of permutation matrices. So which is permutation matrices are a subset of GL, a subgroup of GL and C's. So it's kind of the same statement. Cayley's theorem is usually a bit stronger. But don't worry about that for now. For now, the statement is basically if you look at finite groups, you can always find them in matrices. It's not like they're always immediately of the form SL or something else. That would be too good. No, it's more complicated. But at least they're subgroups of matrices. And the way this is usually proven is actually pretty easy and very, very, very nice to see. So you write down the multiplication table, and I told you that's something you shouldn't do, right? That's kind of my whole idea. Don't do that. But just think of course, you could always do it. So just think we can do it. We write it down, and from the multiplication table, we can actually read off the subgroup of GLN. And the point is, this n is really this n, is this n, or is this n in this case. Oh, this was a little bit too big. This n in this case. So I can read off 4x4 matrices from a 4x4 table. How do I do that? Well, I just look at, so the entries, let's say the 0, 0 entry appears somewhere, it appears once per row and column, and I write down the corresponding matrix. Whatever, the 1, 1 entry appears here, it's a red one, and I write down the corresponding matrix, and so on. So here's my, what is it, purple one, and I write down the corresponding matrix. And the remaining one is this whatever orange type thing, maybe brown, whatever it is, and I write down the corresponding matrix. So it's actually a very easy idea. Well, in that sense, certainly matrix groups are the most important groups. But there's another reason why matrix groups are the most important groups. Here I just told you, well, okay, all groups actually, or all finite groups, not all groups arise in this way, by the way. But to have counterexamples, you have to get already pretty fancy groups. They're all infinite, for example. Anyway, all finite groups are certainly linear. So all finite groups arise as subgroups of GLN, which is a pretty nice statement to keep in mind. Yes. So what I wanted to say is, so there's the so-called periodic table of finite simple groups linked in the description below. And basically what this table is saying is that in some sense, all finite groups arise in this way as some SL, GL, whatever over a finite field. That's of course not quite true. You know examples of groups that do not arise in this way, cyclic groups, for instance. But it's quite true in a certain very precise sense, which you can actually find in this periodic table, because most, columns of that periodic table are of the following form. There are GLNs, there are SLNs, or a finite field, or something like orthogonal groups. Product of orthogonal matrices is an orthogonal matrix, so they form a group. Symplectic matrices, so product of symplectic matrices is a symplectic matrix, and so on. So these things. You don't really need to know what orthogonal and symplectic matrices are if you don't remember anymore from linear algebra. You can look it up. It's worthwhile to know. There's a certain list of matrix groups that you can use here as your building blocks, and just feed in a finite field and you get a finite group. So here, for example, is the order of GLN, FQ, and this product just explodes. So for GL2, I've written it down. So Q in our example was 2. So let's have a look. 2 squared minus 1 is 3. 2 squared minus 2 is 2. 3 times 2 is 6. Yes, that was the example from before. For SL, I did the same. Here you go. And this is then the formula for SL2. So let's have a look. Q was 3 in my example here. So let's have a look. 3 plus 2 is 4. 3 squared minus 3 is 6. So 4 times 6 is 24. Yes, works. And as you can already see, this grows very, very fast, right? It grows basically of order 4, because you have a Q and you have a Q squared and you have a Q squared. So the next one is already pretty big. And that might be the reason why people usually don't show you those matrices in the first class on group theory, because you kind of want to work with small groups. But in some very precise sense, link is in the description to this periodic table, basically all finite groups are of that type. They just start pretty late. So any kind of statement you have in mind about finite groups, you should double check them with those matrix groups. And they're not so bad. They're matrix groups after all. They're just big, right? They're not bad. They're just big. Big doesn't mean bad. Of course not. A fun fact, and then I'm done, is that Galois himself actually has discovered those groups a long time ago, which makes it kind of clear why those, well, not really, but it kind of explains why these are very natural groups. Of course, people knew symmetric groups or cyclic groups before. What I mean here is, in the sense of group theory, GLN FQ was one of the first groups ever discovered. Yeah, so Galois discovered them, and he wrote a letter to Chevalier, I think, in roughly around 1832, which is a long time ago. That's almost 200 years. So this is a very natural family of groups. Not just because Galois has discovered them, which makes them pretty nice, of course, which is, of course, a pretty nice fact, but also I hope I convinced you that automorphisms and matrix groups and whatever, they are just very natural objects to study. Anyway, so that's it for today. I hope you enjoyed the video. Let me wrap up the video. Basically, what I'm trying to explain is that you have this very natural family of finite or infinite groups, namely matrix groups of a certain field. You can play around with them a little bit. You don't have to consider GL. You can consider SLN. You can consider orthogonal matrices, practic matrices, or some variant of those. And you get some nice groups, and they are pretty natural. So yeah, as I said, I hope you enjoyed the video, and I also hope to see you next time.